Okay, so our next speaker is Katey, and she's going to tell us about something we haven't heard very much of so far this meeting, molecular outflows in AGN and ALMA.
So Preeti, thank you to all the conference organizers for inviting me to this wonderful conference. I have to say I'm very, very happy to be in India for the first time, although I'm going to be very disappointed when I get back to California and have to eat California dosas rather than Bangalore dosas. So this has been a really interesting meeting for me, given that the vast majority of meetings I've been to on things like AGN feedback, radio galaxies, jets, have been, let's say, 80% galaxy evolution and 20% jet physics. So this has been really, really enlightening, given that this meeting, I'd say, is opposite. And it also meant that I thought very carefully about taking on the great power and the great responsibility of being your speaker to bring you into molecular outflows. But I want to start with galaxy evolution, because that also seems to be something that we should have a little talk about. So what I have here is I have the way galaxy evolution extragalactic people define galaxies. On this side, we call the galaxy a late-type galaxy. And if you're a stellar evolution person, this is actually the opposite definition. Late-type galaxies are spiral galaxies. They tend to be star-forming. They tend to have gas. And early-type galaxies tend to actually be defined by the evidence of absence. That is, early-type galaxies tend not to have spiral structure. In Z of 0, in the modern universe, there's something really important about this picture, which is galaxies that transform from late type to early type tend to be going on a one-way path. This means that understanding the conditions by which galaxies transition across from late to early is really important. And there are a lot of ways they do that. Mergers is a really excellent way. Falling into a cluster appears to be a very good way, although there's now starting to be evidence that group preprocessing actually happens before, group preprocessing as a galaxy falls into the cluster is actually what transitions that galaxy. Secular evolution seems to be able to do it. That is, a galaxy can grow its bulge so large that it becomes stable against gravitational collapse for its molecular disk. And finally, again, why are we here at this meeting? It's because we're talking about AGN feedback. So why is it in the first place that we care about AGN feedback? Well, there are a lot of reasons, and I'm lucky that I am actually going after Laura Bergeon's wonderful talk, so I don't need to show you a lot of these motivations. One of them is that black hole masses and bulge masses seem to be correlated. But the one that comes into the kind of feedback that I'm going to be talking about, which is quasar feedback or radiative feedback, or potentially just feedback from an AGN that's driving molecular gas out that isn't in the center of clusters, is because if you don't have AGN feedback, you have far too many large galaxies. So what I'm showing here is I'm showing the difference between the observed galaxy mass function and the one that comes out of a simulation. And what you can see is that the observed has far fewer galaxies at this large mass. So the way that people were able to truncate this was by saying, okay, why don't we see what happens when we turn on an AGN and let that quench the star formation. So that's what they did. When I'm talking about AGN feedback again, I'm talking about the kind of AGN feedback that this beautiful simulation by Volker-Springel will show you in just a second. So I want you to watch, this is the gas. So what you're going to see fairly soon is you're going to see points when the AGN actually turns on like that and blows the gas out of the system rapidly and prominently. So what this is able to do is by blowing the gas out and blowing the gas and heating it and putting it in the halo as X-ray gas, it removes that gas from the system and does not allow that gas to form more stars, i.e. truncating the galaxy mass distribution. So the generic picture that people came up with to explain quasar feedback looks something like this. And I'm using the merger analogy here in particular. So galaxies coalesce. And what is important is this step right here. This is the AGN feedback step, the blowout stage, which then opens up and you start to, then the quasar becomes unobscured. We tend to see the quasar phase. Then you get to the K+A phase, which is actually the post-starburst phase. And a post-starburst galaxy is a galaxy that has evidence of young stars, but no current star formation, because that star formation was cut off recently. And finally, that's how this particular schematic models how galaxies evolve. So that's wonderful. The thing is, if you have just this statistical evidence that something had to truncate galaxy star formation, you can say, well, maybe this AGN feedback thing will work, but that does not necessarily mean that you have observed it. And so when we knew this was a responsibility that observers had, we had to start looking for evidence of AGN feedback in the form of outflows. So what I'm showing you here is I'm showing you some of the first signs that AGNs had really strong outflows. And the great news is I don't have to do much more on this because a lot of this meeting has talked specifically about these kind of things. So I'm going to talk a little bit more about the phases that are carrying a larger bulk of the gas out, starting with ionized gas. So people also started seeing when we started getting integral field spectrometers, they started seeing outflows from AGNs in 03 when they pointed and looked very deep. More recently, it turns out work from Dave Alexander's group by Chris Harrison in particular started doing this more systematically and looking at a large sample of normal star-forming AGN hosts. And what he found was that when he looked at 03, he found that outflows were a near ubiquitous property in these galaxies. So that's great. That means if you have an AGN, it is very, very likely you have an outflow. But I'm talking about the ionized gas. And we all know the ionized gas might help trace sort of the edge of the mass, but that is not where the mass is. That is not where the star formation is. So you had to go denser. Next, people actually started seeing evidence of outflows at H1. What I'm showing you here is actually work by Raphael and Morgan. I picked IC5063. Those of you in the room who are radio galaxy experts, which is all of you, very likely know about the large sample of radio galaxies where Raphael is finding exactly what I'm showing here, which is that when you look at the H1 absorption against the radio source, what you see is a blue shifted wing. More recently, looking at ULIRGs, Herschel actually found something surprising. I don't think that this was expected. They found that when they looked at many, many ULIRGs, they found P Cygni profiles in the OH emission, which is getting to be a pretty dense gas tracer, which was a sign that there were outflows. But again, I'm not talking about Herschel. This is not the role of Herschel. This is not the role of the VLA. This is the role of ALMA. So I'm talking about molecular outflows. The first bona fide AGN-driven molecular outflow detected in CO was Markarian 231, found by Chiara Ferrulio. This is a Plateau de Boer spectrum. And what you can see, the reason it took us this long to do this in CO is actually because we had to wait for the technology to catch up to us. We needed really, really broad bandwidth, which meant we needed sophisticated correlators, very good receivers, and really stable baselines to remove all of those wiggles, to see these tiny little wing effects. So once Markarian 231 was found, Karma was actually the one that was able to resolve the lobes to start to actually get an idea of the mass outflow rate. And work by Suzanne Alto has shown that this is not just an optically thin CO outflow. This is actually an outflow you're seeing in dense gas. So 2010, we had one AGN-driven molecular outflow found. 2011, 2013. In the last 5 years, this field has exploded. So there have been another 15. I actually think I'm out of date now, given that I think IC5063 has been found to have molecular outflow. In fact, I think there are also a couple of Z of 2 quasars that have been found to have molecular outflows. Seems to show that this first ionized gas ubiquity might actually apply to AGNs as well. For me, the galaxy that really convinced me was this right here, which is Santiago Garcia Barrio's observation and detection of an outflow in NGC 1068. When the most nearby Seyfert-2 has an AGN-driven molecular outflow, you can start to say that this is probably not a rare phenomenon, this is probably a common phenomenon. But to be controversial, that also says something fairly significant. So back 2011, when I found NGC 1266, I said, wow, look at this galaxy with this wonderful AGN-driven molecular outflow. We have caught this galaxy in this very special phase in its evolution. Because if you look at the gas and you looked at the mass outflow rate, what you found was there's 10 to the 9 solar masses of molecular gas. The molecular gas is coming out at 100 solar masses per year. You're supposed to get rid of all of the gas in 10 million years. That means that every time we see one of these molecular outflows, we're seeing it in a snapshot in the galaxy's life. Except that means that every time we're observing and we're careful looking at the kinematics of that molecular gas, we've seen a lot of snapshots, and we seem to have a ubiquitous set of snapshots, which I think was wrong. So let me tell you a bit about NGC 1266 and how the paradigm of how molecular outflows work, at least at z of 0, which you notice was my one little asterisk, works. So NGC 1266, the beginning of this game, appeared to be a quiescent S0 galaxy. All the ground-based observations basically didn't show any interesting structure. The reason you're seeing structure here is because we finally had to go to HST. But it hosts a massive molecular disk, a massive molecular outflow that is multi-phase. It has an AGN. It has a young stellar population, but not an infant stellar population. And it doesn't appear to have any signs of a major interaction, though there might be signs of a minor interaction. And something that is actually quite important is star formation in this system is suppressed by a factor of 50 to 150. Now, when I say the word star formation suppression, I mean something very specific. Star formation suppression is not the lack of star formation. It is a case where you have a large reservoir of molecular gas that is not forming stars at the rate that it should by some factor. And in the case of NGC 1266, it's large. So when I say NGC 1266 contains an AGN, what I mean is we pointed the VLBA at NGC 1266 to make sure that there was a peaked radio continuum point, and we found one, which was great. And at the point that you get to 1.5 by 10 to the 7 Kelvin, only a very extraordinary supernova can do this. Jim Condon has shown theoretically that you can't get it above about 10 to the 5 Kelvin from an ultra-compact starburst. So this is great evidence that NGC 1266 has an AGN. Whether it's an energetically relevant or an energetically irrelevant AGN is completely different, but we know there's one there. NGC 1266 contains a post-starburst stellar population, another fairly important point. So when we looked at this system, we age-dated the stellar population. We found that the youngest stars that we could see from the absorption were about half a gigayear old. And that was also shown by the UV data, which you can see here, as well as the H-beta absorption, which also traces this A-star stellar population, so these intermediate age stars. And we compared the size of the A-star disk to the size of the current site of the molecular gas. And what we found was that they're about a factor of 10 off from one another. That means something happened half a gigayear ago. There used to be molecular gas out here half a gigayear ago, but now there's only molecular gas here. So that was really interesting, given that it told us a little bit about when an interaction might have happened in this system. It didn't happen very recently. On top of it, we have ultra-sensitive observations to look for stellar tidal tails. We actually also have this in H1. And what you can see here, this is ultra-sensitive work by Megacam by Pierre-Alain Duc, which gets down to 29 magnitudes per square arcsecond. He's really pushing down to really, really deep sensitivities. And what you can see is that this right here is the only sign that anything might have even gone on. This is the only sign of maybe a tidal tail. A major merger, half a mega year ago, you would see shells all over the place. This system would not look like this. So that might mean a minor merger happened that drove the gas into the center half a giga-year ago. So NGC 1266 contains a massive molecular outflow. This was the first system in the AGN-driven molecular outflow game that we actually were able to resolve the high velocity structure. This was what the spectrum looked like. And what you can see up here in this picture is I've actually summed up this large velocity and this large velocity to create the lobes. And what's great is you can see that it has a nice structure where the lobes look like they're coming out of different sides of the systemic velocity at the center. And that cross right there is the point of the VLBA point source. So the molecular gas, there's about 4 × 10⁹ solar masses of molecular gas in the system. The outflow is a few by 10⁸ solar masses, which means the outflow mass flux is 110 solar masses per year. And it looks to be the dynamical time, that is the amount of time the outflow has been on, is less than 3 megayears. Now, that should mean that we've seen this in a special stage. This also should mean that this is a very transient phenomenon in this galaxy. But when I looked at statistics, we shouldn't be seeing transient phenomena in every galaxy we look at. So there was something wrong. So we thought about it. That's when we detected, and we detected HCN in the outflow. So you guys can trust me when I say 110 solar masses per year. This is not an optically thin molecular gas situation. But there's something else about this that should be really interesting, which is this does not look like a regular rotating disk. In fact, if you look at the imaging of this galaxy, it doesn't look like a regularly rotating disk either. So we realized we needed to change the way that we talked about it. In fact, future me went and looked at past me and said, this isn't a special time, Katey. Sorry. Because most of that gas is not exceeding the escape velocity of the galaxy. In fact, only 2% of the molecular gas is exceeding the escape velocity in the galaxy. That means that the depletion, that is, the amount of molecular gas that is actually exiting the system in such a way that it is not going to be able to come back and form stars, is 2 solar masses per year, not 100 solar masses per year. And if we look at all of the molecular outflows that have been detected at that 15 that I showed you, and you start to actually factor in the escape rate, you're finding that the outflows are not these extraordinarily massive things. In fact, you're finding that there's something even worse happening, which is that these systems are pumping up all of this molecular gas, giving it all of this kinetic energy, driving it out just a little bit before it falls right back in and re-inputs that kinetic energy it gained back into the molecular disk, which means you've now fought against the other side of depletion of the molecular gas, which is star formation. So what I'm showing here is the Kennicutt-Schmidt relation. As I said, I know that I'm in a talk full of jet experts, so I'll explain what I'm plotting here. So in 1998, Rob Kennicutt plotted the star formation rate surface density compared to the molecular gas surface density, which showed a really nice relation that showed that basically stars were formed at a constant efficiency over a time scale. Now, the way that Kennicutt 1998 did it was he said it was over a dynamical time. Mark Krumholtz just recently updated this and actually said that this was over a free fall time. But that's partially why this is so consistent, is it seems that star formation is forming at about 2% efficiency in all systems. Except for one. Well, actually, in my own work, we're finding more, but one for now. NGC 1266 falls here. We worked very hard to make sure that we were careful enough to get a star formation rate accurately and a gas surface density accurately for this system. Because the first thing you do is you see something this far off of the common plot and you say, okay, what did I do wrong? But what we found is that everything we looked at showed that the star formation in the system was underforming stars by at least a factor of 50, which means that you actually can hold the 10 to the 9 solar masses of molecular gas in this system for much longer than you think. Because if the system is depleted, if the system is suppressed by this much, you're not depleting that much molecular gas by letting it flow out, because only about 2% of it is actually escaping the galaxy. You're also not letting the gas form stars. So that was really interesting to us. And it made me think, potentially, we need to shift the paradigm we were thinking about with these AGN feedback at z of 0 to something different. Because it didn't look like we were in this case where we had this massive blowout phase that got rid of everything really, really rapidly after the quasar phase. It looked like something else was happening. And I'll talk about this in NGC 1266 in particular, and then I'll tie it a little bit into some of the observations people have done of quasars. So half a gigayear ago, we think a minor merger collapsed a subcritical molecular disk in NGC 1266. That's why you see stars out at 2 kiloparsecs and the gas all in the center. That drove the gas into the middle. And again, it formed young stars. Those stars began to age. The gas was continuing to collapse towards the AGN, which ignited the AGN, turned on the radio jets, which are currently driving the molecular outflow, suppressing star formation and injecting turbulence. So we think we're right here. Now, at some point, one can predict in the future, the AGN is going to stop being fueled. The radio is going to turn off. The outflow is going to fall back into the nucleus, going to re-inject turbulence, but turbulence is also going to dissipate. So star formation is generally just a balance between energies. You have the gravitational potential binding energy on one side, and you have kinematics, turbulence, radiation, pressure, et cetera, on the other side. So what we say is that in this system, we're adding an external amount of kinetic energy by adding and injecting new turbulence into the system. And that is why gravity is not winning the battle. It's not 2% efficient right now. At some point when the turbulence dissipates, we should turn star formation back on, because gravity is going to start winning. But it's going to start winning not only in star formation, it's going to start winning and letting gas fall back into the AGN, which potentially is going to reignite the radio jet and cause a duty cycle in this phase right here, where there's gas in the middle. It turns on this molecular outflow that suppresses the star formation, and then at some point that all collapses back in, and there's just a blob of gas sitting right in the middle again, and then it turns it back on, et cetera, et cetera. And it turns out this story actually fits the stellar populations one sees in quasars. Katey Alatalo has some really great work on stellar populations of quasars, and what she sees is that quasar stellar populations tend to be A-star stellar populations, half a gigayear stellar populations. So that means that we're not driving and blowing all of the gas out right away. We might actually we need to have mechanisms that can maintain the gas in the center. And the AGN outflow is a good way to do it. Now, believe it or not, I'm a little bit excited that it seems that I've run, not even on time, but 2 minutes early, so I actually get to talk about my conclusions. AGN feedback is a well-known problem. We need to figure out a way to not form over massive galaxies. This was a good way to do it. And again, I'm not talking specifically about what happens when you're looking at z of 2, which is where Nadia Zakomska is seeing quasars that have energies of 10 to the 47 ergs per second, which might actually be getting substantial enough that you might be able to decouple molecular gas in the whole system. AGN is actually removing gas from the systems. It's depleting gas, but not as fast as we think. That is why it is okay that we're seeing these ubiquitous molecular outflows in AGNs that, again, have molecular gas near them. It's because this is not something that is just flashing away all of the molecular gas in an instant. And at least for me, the duty cycle that I described, where basically you get stuck in this zone where you're blowing just a little bit of the gas out, it's collapsing, turning on the radio jet, turning off the radio jet, turning on the radio jet, turning off the radio jet, might actually be something that works for NGC 1266, but potentially it works for other galaxies too, because we need to reconcile the stellar populations in quasars with the energetics that we're seeing and the outflow rates we're seeing. So I would argue that using the escape rate rather than the outflow rate in these systems to describe how long it takes to deplete the molecular gas is probably a more accurate way to think about it. And at that point, I'm done, and I'll take questions. Ooh.
Loads and loads of time for questions, so let's... Okay, yeah.
Very nice results, Katey. You just give nice observational confirmation of the simulations. I'm going to show 2 talks from now. One comment and one question. Comment is, you showed the Nicole's results as well as Raphael's results on IC 5063. So the amount of gas that you can eject out of the galaxy, so Nicole gets very high velocities of 1,000 kilometers per second, but that is a function of is a redshift as well as the density. As well as Raphael gets very slow velocities. So I completely agree with your idea that some jets will not really be driving gas outside the galaxies, but bear in mind it's a function of the jet power as well as density. And the question was, what is the mechanical power of this source that you mentioned?
Oh Lord, I think it's probably in my 2011 paper, but I don't want to be that cagey about it. I think it's a 6 by 10 to the 42, 10 to the 43 of order.
Okay, it's a low-powered jet.
It's a low-powered jet, yeah.
Thanks.
Go.
Okay, the idea of this duty cycle. The picture that comes into my mind when you describe it, not knowing really the first thing about electrical molecular outflows, except that you just told me a little bit, is that, I mean, when you have this stuff basically sort of coming crashing down, does it have time to actually form some stars before it gets reignited and goes back out again? I mean, is it possible you could actually have sort of quasi-periodic star formation associated with this? And is there any way to look for that observational evidence of that?
Ooh, to answer your first half of your question, yeah, we would definitely expect to see quasi-periodic star formation. To answer the second half, I think given the new technology coming in, like the new telescope technology, for instance, things like MUSE, we might actually have the resolution to dig down into these ultra-compact little knots of molecular gas to see if we can do a little bit better on the star formation history, to look for, again, signatures of things like O-stars. NGC 1266 is particularly difficult because on top of being an AGN, it's actually a Compton-thick AGN. So you're kind of anything that might be going on that's interesting is happening below the tau equals 1 surface of the gas.
Okay, over there, and then I know.
Hello. Yeah. Could you please show the dust picture again, dust silhouette of 1266?
Let's see.
So we see actually only 2 clumps of red-shifted and blue-shifted molecular gas.
Right.
So there must be that much more than this all surrounding the thing. We are missing the large part of this. So my question is, does this dust is actually also flowing out like a biconical structure? I know
Yes.
this picture. This is
On top of it,
H-alpha radio picture.
So is H-alpha, so is radio continuum, so is X-ray.
Yes, what?
So I'll point out, actually, so this is, these data are in a paper by Tim Davis. It's really wonderful from 2012 on this source. So yes, we think the dust is going out. We know, for instance, we absolutely know that there's neutral sodium deabsorption in this source, which would be sort of tracing the same interstellar material as the dust. So yes, we do think the dust is taking part in the outflow, but when I said the outflow is multi-phase, I mean it. Every single ionized gas line looks like this. I think I picked S2. I could have picked N2, O1, O2, O3. I don't think we have O2, 37, 27, et cetera. They all look exactly like this. And the thing that we thought was great is that we were detecting the shocks in radio continuum. I don't think that these are the jet. I think that those are probably actually coming from the shocks that are taking place in this outflow. It's a weird system.
Yeah.
A blessing and a curse for a young graduate student.
How do you know those aren't the jets? Because of the way, I mean, when I look at that, I see a double source.
We don't. There is one way to find out, which is you can look at the spectral index of that thing to see if the spectral index gradients are there. And we have Eric Murphy and I have a student named Dylan Dong who's working on doing that with a very large swath of data we have in the radio.
Cool. I know.
Actually, I wanted to continue here. Are we 100% certain that actually the jet is really depositing the energy and driving the outflow? That would be fantastic because it gives meaning to all what we do here, right? If I remember work on C4 galaxies we did, you see outflows, right? And you sometimes wonder, okay, and it's aligned with H alpha gas and other things, but is then the jet driving it, or is actually the jet or the outflow modified by the outflow? And then, of course, also the radiation is going along the axis because of the torus and so forth. So there might be, other mechanisms which deposit energy and drive the outflow. Can you exclude that?
Energetically, actually, so. Again, I hate pointing to my paper only a little bit. I like it too. In my 2011 paper, we actually worked really hard to look at energetic arguments as to what could create enough mechanical luminosity to drive this. There's not enough radiation in the system, so it's certainly not a starburst-driven wind, because that's immediately the first thing you look into. There's just not enough star formation. There are not enough supernovae. Something that Martin and I were talking about, I think last night on the bus, is the possibility that maybe some of the work that we're seeing in here could be cosmic wave driving, especially the suppression. I'd say overall, every idea we had to try to drive this energetically got shut down, except for letting a mechanical luminosity of the jet drive the gas out, because the coupling was either too high. The coupling I think you needed for the radio jet was something like 5%, which is sort of right in the range that you need. And if you want to look a little bit more on sort of energetics of the radio jet itself, it would be in the Christina Nyland paper from 2013.
But sometimes there are also AGN winds, which are not really jets.
Right. So again, the thing about it is if star formation if radiative power from star formation can't drive the outflow, there's also not going to be enough radiative power from the AGN. I think we went straight out of Norm Murray's work to show that there isn't enough L to couple the angular momentum properly.
Okay, one final question.
So the picture that you showed in the last slide, it kind of follows from one thing. It's kind of natural, but then why is it not statistically significant that you expect this kind of sources? Like I'm saying, why don't you see this in more sources?
Because it's hard. So that's not the only part of the answer I'll say. So what I was saying before, finding AGN-driven molecular outflows was something we only started being able to do in about 2010, because that was when the instrumentation caught up with what we wanted to do. These are features on the edges of CO lines that at the best are 10% of the peak luminosity, and at worst, I think some of the sources from Claudio Ciccone were 1/1000th the intensity of the peak. So you're looking for very, very low surface brightness, low sensitivity features to find these. And in the case of NGC 1068, it was basically based on the care of Santiago, where he was able to decouple all of these ultra-complex kinematics of the molecular gas in the center of NGC 1068, where he was finally able to isolate that outflow piece. So combining those three things, you need the sensitivity to do it, which means ALMA is going to be great. You need the instrumentation to do it, which means ALMA is going to be great. And you need people who are extremely detail-oriented to look at the messes that are some of these systems. Luckily, there are plenty of people who do that. Will be why we're probably going to keep finding more. And every month, there are going to be at least another couple of new AGN outflow discoveries.
On that positive note, let's thank Katey again.